Could a seemingly ordinary magnitude 4.7 tremor tell us something profound about California's earthquake future? Or was it simply the latest jolt from a region that rarely stays quiet for long? The answer may lie not in the size of the earthquake itself, but in where it struck and the violent swarm unfolding around it. At approximately 0710 Coordinated Universal Time on May 10, 2026, the United States Geological Survey located a magnitude 4.7 earthquake at a depth of 13.7 kilometers, or about 8.5 miles, beneath the Imperial Valley near Brawley, California. The epicenter was positioned roughly 4 kilometers, or about 2 miles, west-southwest of the city, directly inside the highly active Brawley seismic zone. That location immediately drew scientific attention because this was not an isolated rupture. The earthquake erupted in the middle of an intense swarm sequence involving hundreds of smaller tremors clustered tightly across the region within only a matter of hours. Why did this swarm suddenly ignite here? And what do the earthquake signals reveal about the forces breaking apart the crust beneath Southern California? Those questions matter because the Brawley seismic zone is one of the most tectonically complex and mechanically stressed regions in North America, where major strike-slip faults, crustal rifting, geothermal activity, and deep plate boundary forces all converge within the same unstable corridor. The raw data paints a clear picture. The Brawley swarm had already produced dozens of magnitude 2s and 3s shocks when the magnitude 4.7 struck. Seismograph network waveforms show this main event was a textbook strike-slip earthquake, meaning the Earth's crust moved horizontally past itself on a steeply dipping break rather than thrusting up or down. The focal mechanism diagram for this event confirms that both candidate fault planes are nearly vertical, with slip vectors almost purely horizontal. In other words, the rock slipped sideways, exactly what one expects where right lateral transform faults dominate. The aftershock pattern only underscores this interpretation. The nodal planes are near vertical and the rake angles are about 4 degrees and 173 degrees, essentially flat slip. That is pure horizontal motion, like cards shuffling, not a vertical push or pull. This match makes sense because scientists long ago identified the Brawley area as a transition zone between the San Andreas and Imperial faults, so horizontal shearing is normal here. But the real story is the swarm. This magnitude 4.7 was not a lonely main shock. It was the crescendo of an earthquake swarm. By late Saturday, May 9th, seismologists had recorded well over 100 tremors in the region, clustered in a tight area west of Brawley. Local news reports noted more than 100 earthquakes rattling Imperial County that evening, including multiple magnitude 3s shocks and even a prior magnitude 4.5. One California station counted over 150 quakes in the span of a few hours, ranging from tiny microquakes to magnitudes in the mid-4s. Crucially, unlike a typical California sequence with one main shock and smaller aftershocks, this pattern was a swarm, meaning many mid-sized quakes happening together. The largest shocks, including magnitudes 4.0, 4.4, 4.5, and finally 4.7, were not vastly bigger than the background tremors. Instead, they piled up in a matter of hours. As ABC7 reported, all ended up being foreshocks to the magnitude 4.5 event Saturday night. Foreshocks in a classic swarm sense, not main shock-aftershock behavior. Around Los Angeles, you rarely see a small magnitude 3.5 followed by dozens of similar quakes. Most California earthquakes are solitary events with decaying aftershocks. Here in Brawley, swarms like this are typical, with lots of events at once and many close to the largest magnitude rather than one main shock. USGS seismologist Lucy Jones even noted that Brawley sees lots of events at once, and that swarms are typical for that area. Why does the Brawley zone swarm? Geology explains the frenzy. This is not a gentle fault at all, but a tectonic hotspot where a strike-slip boundary transitions into a rifting zone. Think of it as the northern end of the Gulf of California rift, where the Pacific and North American plates are pulling apart. The crust here is being stretched even as it slides, a kind of twist and pull. Geologists describe it as partly a transform fault system like the classic San Andreas and partly a continental rift like the Gulf Spreading Center. The Brawley seismic zone is a predominantly extensional tectonic zone that connects the southern terminus of the San Andreas Fault with the Imperial Fault. In plainer terms, the mighty San Andreas Fault ends north of Brawley and transfers its motion to the Brawley and Imperial Faults, while the crust is also being pulled open like a zipper. This geometry creates two pull-apart basins right in the seismic zone, wedges of ground dropping down where faults step over one another. The map of the region shows them clearly, one basin at Neeland hosting geothermal fields and another at Cerro Prieto, an active volcanic and geothermal site. In effect, right lateral slip is actively pulling the ground apart at those stepovers, feeding magma and hot fluids into the shallow crust. Not surprisingly, the Salton Trough around Brawley is riddled with volcanic and thermal features. The Salton Buttes volcanoes on the north shore of the Salton Sea sit right on this zone and are linked to volcanic and geothermal activity. Seismologists even describe the entire Brawley area as behaving like an onshore spreading centre, essentially the continent just north of a mid-ocean ridge. That means magma and hot fluids are present, weakening the crust and making earthquakes easier in unusual ways. It also means intense fracturing and heat flow, which in turn spawns swarms of shallow tremors. In short, this is one of the busiest kinds of fault systems imaginable, both sliding and splitting at the same time. All these factors explain why even moderate quakes in Brawley grab scientists' attention. The southern San Andreas Fault proper actually ends just north of here. It does not continue straight through Brawley. Instead, its motion transfers into this complex network of faults and rifts. So, although the big San Andreas Fault does not break directly under Brawley, the stress from the Pacific Plate must go somewhere, and this is where it does. Geologists often describe the Brawley area as a mechanical bridge or hinge between major plate boundary faults. It is like a crossroad where the great strike-slip fault system meets a continental pull-apart intersection. That does not mean each small quake is directly telling us about the big one on the San Andreas. A magnitude 4.7 is far below what would be considered a megathrust scale event. But it does mean every jolt slightly changes the regional stress field and must be carefully monitored. In fact, this area has hosted some of California's largest historical earthquakes on nearby faults. The Imperial Fault, just to the south, ruptured in a magnitude 6.9 earthquake in 1940 and a magnitude 6.5 earthquake in 1979. Both times, rupture extended partly into the Brawley zone for about 13 kilometres, 8 miles. Within the Brawley zone itself, past swarms have also drawn attention. A 2012 swarm produced hundreds of earthquakes, with the largest reaching about magnitude 5.5. Even a 1981 swarm produced a quake up to magnitude 5.8. So the potential for stronger shaking exists, even if it is not guaranteed. The focal mechanism of this magnitude, 4.7, offers additional clues. Because the nodal planes dip almost vertically, around 83 degrees, and the rake is near 0 degrees or 180 degrees, nearly all motion was shear along strike. In practical terms, the earthquake likely slipped on a buried near vertical fault segment, moving side to side. This was not an explosive type of failure and not a vertical thrust or normal fault motion. It was pure horizontal motion, exactly the style expected in the Brawley seismic zone's transform fault setting. One interesting detail is that analyses suggest this event's seismic moment tensor contains only about half of its energy in the double couple component, which represents pure fault slip. The remaining portion includes non-double couple components, such as compensational linear vector dipole and isotropic signals. In many cases, a low double couple percentage can indicate a complex rupture process or mixed mechanisms, sometimes influenced by fluids. That would be consistent with the Brawley environment, where geothermal fluids and aseismic creep can complicate fault behavior. Researchers studying the 2012 swarm found evidence that quakes were preceded by slow aseismic slip beneath geothermal fields, likely influenced by fluid movement. That sequence also involved unusually shallow and high-frequency seismic activity as a result. In other words, moving or pressurized fluids can reduce friction on faults and help trigger earthquakes. It is not yet known whether fluids played a role in the 2026 swarm, but the historical context makes it an important possibility to consider. What comes next is difficult to predict with precision. Swarm earthquakes are notoriously variable, but patterns in this region suggest the most likely outcome is continued activity. Hundreds of aftershocks over days to weeks, mostly in the magnitude 2 to magnitude 4 range, are typical. Additional magnitude 4 plus events are possible because swarms can occasionally produce multiple similar-sized peaks rather than a single dominant main shock. However, most swarms in Brawley eventually fade without producing a significantly larger earthquake. For example, the 2012 swarm remained below magnitude 5.5 overall. Seismologists will focus on how the aftershocks decay and whether stress transfers to nearby faults. Importantly, a single magnitude 4.7 earthquake does not mean a larger San Andreas earthquake is imminent. Swarms are not reliable short-term precursors in most cases. Many simply dissipate without leading to anything larger. As United States Geological Survey scientist Lucy Jones has emphasized in similar situations, there are no reports of damage or immediate threat to public safety, and the main expectation is continued aftershocks. The significance of this magnitude 4.7 lies primarily in its location. It occurred only about 4 kilometers, 2 miles, west-southwest of Brawley, placing it directly within the active fault and basin network of the northern Salton Sea region. This area is one of the most geologically active in western North America, where strike-slip motion, crustal extension, geothermal circulation, and volcanic processes all interact. Every earthquake here provides valuable information. Its depth, mechanism, and relation to surrounding tremors help scientists map which faults are active and how they are connected. In this case, the data strongly indicate slip along a buried strike-slip fault within the broader transition zone linking the San Andreas Fault system, the Imperial Fault system, and the Gulf of California Rift. The swarm pattern helps outline how stress is distributed across this network beneath agricultural land and infrastructure in the Imperial Valley. The key takeaway is that this magnitude 4.7 was not an isolated or random event. It was part of a larger pattern of deformation occurring in one of California's most complex tectonic junctions. For scientists, this makes the sequence highly valuable. It provides a natural experiment in how faults interact where a major transform system transitions into a rift environment. The strike-slip nature of the rupture identifies the fault style. The swarm pattern reveals stress redistribution, and the location highlights how plate motion is partitioned across the region. In this sense, even a moderate earthquake becomes an important data point in understanding how the Earth's crust behaves at a plate boundary intersection. Overall, this swarm reflects the expected behavior of a highly active tectonic transition zone. It is not a clear warning of a larger imminent rupture, but rather another expression of the ongoing interaction between the San Andreas system and the spreading environment of the Salton Trough.